Okay, this first problem's actually not that bad. They give us a bunch of information: the mass, it's at a constant velocity, they give us the height, the time, and the question is the power supplied by the lifting force. Well, if it's at a constant velocity, then the work done is none of it is going to go into kinetic energy. It's just going to turn into gravitational potential energy, which is mgh, and divided by t, and that's it. Okay, in this next question, we have an Atwood machine, and the first part is actually a momentum problem, but the second part is energy, which is why we're going to do this problem. So the first question is, when the speed of the object is v, what's the linear momentum of the system? So we've got a little bit of a problem here because one of them is going up and the other is going down. So I called down to be positive. So the sum of the momentum is going to be, then they're going to have the same velocity because they're connected to each other. So that's going to be minus m1v, that's going to be our up, and our down is m2v. So we just factor out the v, and that gives us m2 minus m1 times v. Now, the second part of this question is an energy question, and it says, when the object of mass m2 has descended height h, the potential of the energy system has decreased by how much? Well, let's look at the change in potential energy. That's going to be m2g times h. That's how much m2 has changed. And then m1gh is going to be in the other direction, so we're going to make that minus. Factoring out the m2 minus m1, that just gives us m2 minus m1 times gh. Another thing to just pay attention to here is that the one object is losing potential energy while the other is gaining potential energy. That's why we're subtracting. Okay, this is question number 4, and what we're given here are 5 graphs, all of force and displacement. So we know that the integral of force with respect to displacement is the work done, and in this case it's turning into kinetic energy. So the integral of f dx, that's the area. Well, which of these graphs has the greatest area? Well, the greatest area would be under graph E, and so that would be the greatest change in kinetic energy. Now, in this problem, I cannot believe this is a multiple choice question. This is so difficult, and if I was taking the AP exam and started to get into this question, I would skip it or at least circle it and come back if you had more time, because it's so time consuming. It could take away from other questions. But basically what you have here is you have this projectile launcher, some kind of like gun or something like that, and it shoots out this projectile and they go in opposite directions. And they're saying that the kinetic energy of the projectile after firing is K. So that's K. And they want to know the kinetic energy in terms of that K going back here. So we call that maybe K prime, or I actually called it KG for K of the gun. So to figure this out, we start out with no kinetic energy, and then we end with kinetic energy. So in other words, energy is not conserved. We start with nothing, then we have kinetic energy. Remember, these are both positive because energy is a scalar. So how are we going to do this? Well, we're going to do conservation of momentum and then be able to get the velocity from that conservation momentum and then sub back in to solve for the energy. So here's my solution. I started out with conservation of momentum and said that the momentum of the gun has to be equal to the momentum of the projectile. But to make it even trickier, they didn't give us the mass of the gun. They just said that the mass of the gun and the projectile combined are m2. So to figure out the mass of the gun, we have to take the mass of the system minus the mass of the projectile, which makes this even messier. So just isolating, we get the velocity of the gun to be m1 vp of the velocity of the projectile, divided by m2 minus m1. So we can then take that and we can sub that into the kinetic energy of the gun. So that's going to be, again, the mass of the gun, m2 minus m1. And subbing that in, you're going to have to square everything. One of the m2 minus m1s cancel. And now we have an expression for the kinetic energy of the gun. But we still have a velocity in there. So we're going to take this equation, and then we can take the kinetic energy of the projectile, which we know is 1/2 m1 vp squared. Now they're just calling it k. I kept it kp. And then we can solve for the velocity of the projectile. So essentially we have the velocity of the gun and the velocity of the projectile. And subbing that back into the kinetic energy of the gun, we end up getting a whole bunch of stuff canceling out. And we're left with the kinetic energy of the gun is m1 kp. That's just k in their problem, they don't have the p, divided by m2 minus m1. Okay, for this problem we have a rock lifted for a certain time by force F that is greater in magnitude than the rock's weight. So if we look at this, we have the force in this direction that's doing the lifting, and the weight of the object, W, that's we've been calling that Fg, is in this direction. So the work done is going to turn into the kinetic energy, but we need the net force. And what's the net force? Because the other force would be that when those cancel out, that constant velocity would be turning into gravitational potential energy. That extra force that does the acceleration is going to be F minus W. So the work done by the net force is what's turning into the kinetic energy. So that's F minus W. Okay, in this one, we have a 10 kilogram body. It's moving along the x-axis. They give us the potential energy of the body in joules by this function here. And the question is, what's the force on the particle at 3 meters? Well, we know that the force is equal to negative the derivative of the potential energy. So we just take the first derivative, and we get minus 12x minus 4. Sub in the numbers, and we get a force of negative 32 newtons, which means it's in the opposite direction. So the choice is B. In this one, we have a ball thrown straight up, and they tell us that the ball has a potential energy of 50, and the kinetic energy is 50 at this certain point that it's been thrown up. So we know that if the potential is 50 and the kinetic energy is 50 at the same time, that the total energy is 100. So they never gave us the mass of the object, so we can do that pretty easily because they said this happened at 10 meters. So we can just do PG equals mgh to get the mass of the block. Now that we know that the total energy is 100, we can say that the potential energy at the top of the throw is 100 joules because it's all potential. It's no kinetic, so the total is the PEG. And then we just sub in our 0.5, and that gives us a height of 20 meters. In this problem, we have a time interval of a constant force giving an average power of 4 watts. And it tells us the average speed. Well, remember that power is work over time, but because work is force times displacement, when we have that displacement over time, that's equal to average velocity. So this problem is just a one step if you make this realization here, and we just put in 4 watts F times 2 to get a force of 2 newtons. In this problem, they say when an object is moved from rest at point A to a rest in point B in a gravitational field, the net work done by the field depends on the mass of the object and what? Well, those positions of A and B. And it doesn't matter if this position of A and B is equal, then the work done is 0 for potential energy. And if it is from here up to here. Again, knowing those positions gives us the height, and the height gives us the potential energy. So the answer is A. This one is a little bit involved, and I actually did this in one of the previous episodes, doing this with two-dimensional motion, but it can also be done with kinetic energy. So we have the object, and it's fired straight up, and it reaches some height h. So what I did was, I said if we fire it straight up, that the potential energy that it gains comes from the kinetic energy of the launch. And they're saying that initial velocity launch, I'm just calling it v0. So that enables us to solve for the height. So now we have the height in terms of the velocity. Now, when it's shot at an angle, that vertical component is sine of 45 degrees. So that's going to be v0 over radical 2. So subbing this back into mgh equals 1/2 mv squared, I'm just putting in this v0 over radical 2 to show that this height is now v0 squared over 4g. In other words, it only goes half as high because we have a 4 here and we have a 2 here. Looking at this problem, you can see we've got a function to the -3/2. So when you see something like this, it almost always is just going to be an integral or a derivative. But let's see what it asks for. It says this is the potential energy, and they're looking for the force. So we know that the potential energy is Br to the -3/2 plus some constant, and we know that force is equal to negative the derivative of u. So we do negative times the -3/2 Br 3/2. We subtract 1, multiply through, and that gives us 3/2 times Br to the -5/2. And here's the adding of the fractions if you wanted to see that step there. Okay, in this one, it's actually pretty straightforward. We have this pendulum. They give us the amplitude, which really doesn't matter. And the pendulum is pulled back to 10 joules. So it's released from rest, which means that's the total energy. So it says when the kinetic energy of the pendulum, what is the kinetic energy of the pendulum when the potential energy is 5? Well, if it swings down here, and 5 joules turns in potential, well then we must be missing 5 joules, which is the 5 joules of kinetic energy. Okay, so we have a non-linear spring here, and they give us the force equation of that spring. And it says where F is in newtons and X is in meters. So what's the change in potential energy? Well, we know that change in potential energy is the integral of force. So we're just going to take the integral of that equation, 40x minus 6x squared, from 0 to 2. Take the integral and throw the numbers in, and you get 64 joules. In this one, we have a block sliding a certain distance down an incline, and the work done by gravity is 300 joules. What is the work done by gravity if the block slides the same distance up the incline? Well, if it goes up the incline, then the force due to gravity is down, but the vertical displacement is up. So it's going to be the same amount of work, but it's in the opposite direction. So that would be negative 300 joules. We did this one before in the circular motion unit, but I just wanted to go over this one more time. We have a ball going in a circle at a constant speed. Well, if the speed is constant, then it's not gaining any energy, therefore no work is done. But we can also say that the direction of the force as it spins in this circle is perpendicular to the displacement at any moment in time. So therefore, at a moment in time, they're perpendicular, so no work is done. Okay, this is another problem where we have a spring, And the spring is nonlinear, it's not Hooke's law, so it's equal to kx squared. And so the work is equal to the integral of f dx. We're doing that from 0 to x naught. So this is a pretty simple problem. K is a constant, we pull it out of the integral, and then we just integrate on x, that should be dx, and that gives us 1/3 kx cubed, and x naught, this goes to 0, so it is 1/3 kx cubed x naught. And lastly, we have a power problem here. We have a 1000 watts, so that's the power. It's lifting this 100 kilograms safe at a constant velocity, so that tells us the work is turning into potential energy. And what's the vertical distance through which it can be lifted in 10 seconds. So this could be mgh. I just did it as fx. And the force to lift it would be g, so that's mg. And they gave us the power, 1000 watts. So that's just 100 kilograms. Now, because it's one of the old AP questions, instead of using 9.8, we use 10. Divided by 10, so the math is super simple, and the displacement comes out to be 10 meters.